Good morning, everybody. So today we're going to talk about carboxylic acid derivatives, starting off by talking about reductions. Now, we talked about sodium borohydride reductions earlier. They will reduce aldehydes and ketones to alcohols, but they won't touch esters. Well, lithium aluminum hydride is stronger and it will touch an ester. So what is it going to give? Can you predict it? Pause the video and try to figure out the product. Okay, here's some choices. Can you predict it now? Well, let's look. So what's going to happen? Well, the hydride is going to go for the carbon of the carbonyl, just like it did in the case of borohydride. And the oxygen is going to this time seek out the aluminum. So we're going to get an immediate reaction. The hydride goes to the carbon, the oxygen grabs the aluminum, and we'll get this intermediate. Now this intermediate is relatively stable until we throw in some water. And if you throw in water as step 2, what will happen, of course, is immediately this thing will fall apart and will form an alcohol. So the reaction is just like sodium borohydride, except because of the reactivity of the lithium aluminum hydride, you have to add the water as a distinctly second step. Otherwise, you could have an explosion. Very exciting. So it gives an alcohol. What about a carboxylic acid? Well, just like water, the lithium aluminum hydride will immediately react with a carboxylic acid, grabbing that proton, and you will make some hydrogen. In fact, you have to be careful if you're going to do this reaction, because you could cause a fire or an explosion of this. So you want to do this in small quantities, add it very slowly in a controlled manner. But now you got this carboxylate. Is it going to react? Well, it turns out that the hydride is reactive enough to react with the carboxylate. So the hydride will again come in, aluminum will again grab the oxygen, and you'll form this stable intermediate. And now once again, you're going to react this, you're going to work this up with water. So you throw in some water, and we actually get an aldehyde. Well, we know what aldehydes do with the aluminum hydride. They immediately go to alcohols. So it'll react further, transfer another hydride, and we'll end up with yet another aluminum complex, which now step 2 will take onto the alcohol. So in the case of a carboxylic acid, you need more hydrides, of course, because the reduction has to go further. So, but the net result is you make an alcohol from a carboxylic acid. And so the nice overall reaction, 2 steps: add the lithium aluminum hydride, then add water. Gives an alcohol. Okay, how about an ester? This one's a little bit more of a mystery because we have to figure out what happens to the methoxy over here. So first step's going to be the same. Here's our complex. Now this is going to be a little bit different because now that alkoxide can serve as a leaving group. So this is going to come back. The bond to the aluminum is going to come back, reform a carbonyl. In fact, it's going to give you an aldehyde, and it's going to kick out the methoxide. Now, of course, your second mole is going to immediately reduce that carbonyl, again giving you an alcohol. So you get an alcohol. But what happened to the methoxy over here? Well, of course, it's sitting here, and so when you throw in the water, it also goes to an alcohol. So what do you get from an ester? Well, you get 2 alcohols. So the reduction of an ester gives you 2 alcohols. 2 alcohols. So let's go back to this problem. This is an ester. This was our first problem on the screen. What it's going to give us is going to give us 2 alcohols. So the carbonyl will become an alcohol, but the oxygen over here will also become an alcohol. So we're going to break the ring, and we're going to get alcohol at both ends. So the answer is D. You're going to get D. This is characteristic of all esters. You get 2 alcohols. If in this particular case it's a diol because it's part of a ring, but if it wasn't cyclic, you'd get 2 separate alcohols. How about an amide? Well, this is an interesting problem. We know what the carboxylic acid is going to give us. It's going to give us an alcohol. But what does the amide do? Well, it's a pretty good chance we're going to get rid of that carbonyl, but how is it going to end up? Here's some possible products. What could we do? Well, you see all of them on the right-hand side have the alcohol. We already did that. We knew that was going to an alcohol. But what about this carbonyl? Does it just go to an alcohol? Does it disappear? Or does it break the bond between the carbon, go disappear and break the bond between the oxygen and the nitrogen. You can imagine any of these happening, but which one really happens? Well, let's look at the reaction in more detail. So here's the amide, simpler one. Bring in the hydride, grab the aluminum. We'll get the same kind of intermediate as we always have. Now what's going to happen? Are we going to kick out that nitrogen? No, we're not. It turns out that the nitrogen-carbon bond is too strong. We're not going to kick it out. Instead, the lone pair of the nitrogen pushes away the aluminum with the oxygen. So this is just kind of the opposite of what we did with the ester, because that nitrogen-carbon bond wants to persist. So we kick out the aluminum, and what we end up with, when you follow all the arrows and do your electron counting, you get this iminium ion down here. Now this, of course, is very susceptible to reduction. It's a cation after all. So another mole of hydride comes in, followed by water, and it takes this down to an amine. So what do amides give? They give an amine. So let's go back to this problem. What does it do? It's just going to erase the carbonyl and give the amine. What's that mean? It means that the product is B. The product is B down here. Okay. So you just have to kind of learn these patterns. Okay. New reaction. And in fact, actually, it's not a new reaction. It's a reaction you had in 321. Synthesis of nitriles. A nitrile, a cyanide, can be formed by using sodium cyanide. Cyanide is a good nucleophile. And here is a nice SN2 reaction. I'm missing an arrow somewhere, but whoops. Somehow the cyanide comes and kicks out the bromide. I lost an arrow, and it gives a simple substitution. Another thing that you can do with cyanide, if you start with HCN, of course all these compounds as are toxic as you can imagine. You certainly wouldn't use these compounds if you weren't an experienced person of handling toxic compounds. But what happens here with HCN? The oxygen is going to pick up a proton, the cyanide is going to attack the carbon, and what you make is something you call a cyanohydrin. So this is two ways of making nitriles. One by substitution, the other one by addition to the carbonyl. Now, the fun thing about these nitriles is you may not actually want those as real compounds, but they turn out to be useful compounds for making other things after you do such things as hydrolysis or reduction. So let's look at those reactions. So here is hydrolysis of the nitrile. Hydrolysis of the nitrile, we're going to protonate the nitrogen. This is under acid conditions, so we're protonate the nitrogen. We have a protonated nitrile. Now that is now susceptible to attack by water. Without the acid, the water wouldn't attack. It'd be too slow a reaction. So you get this crazy looking intermediate. You lose a proton, and what you get here is essentially an enol of an amide. Now that's not a very stable species at all, because the amide down here with all its resonance is so much more stable. So this will quickly tautomerize. The proton will come off the oxygen, then join the nitrogen down here, and you just draw some resonance. You can see what's going on. So it quickly tautomerizes to form an amide. Now amides, of course, under acid conditions, will hydrolyze themselves to carboxylic acids. And it turns out that this first step is harder to do than the second one, because the nitrile with its triple bond is so stable. So it's difficult to hydrolyze an amide, but it's even more difficult to hydrolyze a nitrile. So when you try to do the hydrolysis of the nitrile, you can't really stop at the amide, because this second step, even though it's difficult, is easier than the first one. So the net result is nitriles get hydrolyzed to carboxylic acids. Well, what if you do it under a base? Because we talked about a couple weeks ago how difficult it was to hydrolyze an amide under base conditions. Well, it's very similar for the nitrile. It's still very difficult to do, but again, not as difficult as it's even more difficult than the amide. So what happens in this case? The hydroxide attacks the nitrile directly. This would give you this crazy species. You immediately get a transfer of the proton to give this species, which is similar to now what we called it the previous one looked like a nitrogen analog of an enol. This one's a nitrogen analog of an enolate. That's very basic. It'll pick up the proton from water, go to the amide. And again, amides are difficult to hydrolyze, but not as difficult as nitriles. So this first reaction is very slow. The next one's slow, but faster than the first one. So again, amides will go under proton conditions. Amides will go to carboxylic acids when you hydrolyze. Under basic conditions, they'll go to carboxylate. But in general, nitriles are pretty stable, and it's difficult to hydrolyze them under any circumstance. What else can you do to nitrile? Well, you can reduce it. What does it reduce to? Well, not surprisingly, you just get rid of the triple bond and you make an amine. So you'd add one hydride, go to this crazy looking intermediate, then transfer another hydride to give you this anion with the aluminum on it. And you can imagine this species really wants a reactive water. That negative charge it really wants a proton. Aluminum loves oxygen. So you throw in water and you'll get an amine. So lithium aluminum hydride will reduce nitriles to amines. So this gives us some useful reactions. So what would this product of this reaction be? See if you can predict the product before I show you. We're going to have the nitrile react with a bromide. What's going to do? SN2 reaction. And then we're going to hydrolyze it. What does hydrolysis of a nitrile give you? A carboxylic acid. So the product of this reaction is going to be a carboxylic acid. So we're going to do our substitution. There's our nitrile. There's our hydrolysis reaction. And so this is actually an interesting reaction because it's a way of taking a alkyl halide and making a carboxylic acid 1 carbon longer. Very useful reaction than synthetically. So of course, what's the product? Well, I already told you. It's B. Okay. Well, what if we, instead of hydrolyzing the nitrile, what if we do the same reaction, but then to do the reduction? What does reduction of a nitrile give us? Well, we just did it 2 slides ago. What product are you going to get? You should be able to pick it out. Do the substitution. Do the reduction. And of course, we're making an amine compound B. Okay, here's one that goes through the cyanohydrin. So this one you have to think about a little bit. What's the HCN is going to add across that carbonyl? So it's going to give us a cyanohydrin, which is a compound. Again, it's about look back about 4 slides, and you'll see the cyanohydrin. And what does it do? We protonate the oxygen, add the cyanide to the carbon of the double bond, then we reduce. So we're going to end up with something which has both an alcohol in it and an NH2 group. And what's that going to be? Well, of course, it's going to be A. Lithium or Grignard reagents. Now, what does this have to do with our carboxylic acid derivatives? Well, nothing yet, but we'll get there. So this is a 321 reaction. You did this very early in 321. You add a lithium reagent to a ketone, and you protonate. You get yourself a nice alcohol. So a ketone will give you a tertiary alcohol. Now, what happens if you use an ester for this reaction? Well, this is kind of interesting. If you add an ester, or react an ester with a lithium reagent, we do our addition. We form an O-, and of course, if you were doing a ketone, you'd just be done. You just protonate this. But in this particular case, the methoxide is a good leaving group, so it leaves, and you get a ketone. Now, you could stop there, but it turns out it's really difficult to do. Why? Because esters, with the stabilization from the oxygen lone pairs, are resonance stabilized relative to ketones. That means that the ketone is more reactive to the butyllithium than is the ester, which means this first step may be fast, but the second step is really fast. Indeed, the second step is much faster than the first step, which means you can't stop here. So you'll add again, and you'll end up with a tertiary alcohol. So the addition is going to occur twice. You say, well, what if I'm clever? What if I only add 1 mole of butyllithium? Well, then what will happen is you'll still add twice, but you'll have half a mole of starting material left over. So you just can't get around this. If you're going to do a reaction of a ester with a lithium reagent or a Grignard reagent, it's going to add twice. Now, of course, you can take advantage of this in the synthesis if you know it's going to happen. and just be clever about it. So what about a nitrile? Do you add once or twice? Well, this one's a little bit different because in this case you have nothing to kick out. The butyllithium will add to the nitrile. You'll get an anion, but that anion won't react. This is an anion of an imine. It won't react with a lithium reagent at all, or if it did, it would be a very slow reaction because it's an anion. Lithium reagent is an anion itself. An anion plus anion reaction isn't so favorable. So this one you can easily stop here. Then you work it up with a little bit of acid. You form a true amine. Then you can hydrolyze that water, and you can form an aldehyde. So this is actually something that's good to know. It's you make a nitrile, you react that with a lithium reagent, you make the corresponding ketone. And actually, you could do this. Think of this as two steps. You could start with a bromide, do it in a substitution, and make the nitrile, then add the lithium reagent. So the net effect of what you've done is had, if you had one bromide, could be the left-hand side, go to the nitrile. The second right side could be another bromide, go to the lithium reagent, and you've put together a ketone from two places. So that's all we want to do today, and have fun with the problems below.